Diodes means di means two, odes means that diodes, that there are two electrodes of two positive and negatives are there. That's called diodes. So PN junction diodes. That's only we are going to see that. Before that, that's called PN junction formation. PN, P type semiconductor materials, N type semiconductor materials. You know that what is meant by P type and N type. Now we are going to fuse the P type and N type semiconductor. So PN junction is produced there. So what will happen when the P and the N type semiconductor materials are fused together? That it produces a junction that is called the PN junction. The diode is called PN junction diode. This diode is called PN junction diode. So P-type semiconductor materials, it has large number of poles, that is positive charges are here. This is N-type. N-type means it has large number of electrons are in the N-type semiconductor. So what happens when you fuse together, that electrons are moved from negative terminal to poles. Then poles are moved from positive to negative. They are diffusing. The two electron and the protons are diffusing to each other. So how long it will take place? So after diffusing that, it will neutralize the proton that holds to electron and electrons to hole. So after interchanging that electron and the holes, they are fusing that, they are neutralizing the electrons and holes. Then it is near the junction. It produces the junction that they are accumulated near the junction. They are producing the depletion layer. So it is immovable charges are accumulated near the junction, that's called the depletion layer. That depletion layer produces the potential difference. So when you apply the potential difference between the two layers, you can produce the potential difference. Then after diffusing that electron produce the potential difference, that is called barrier potential. That's called barrier potential. Here, immobile charge carriers are here. So that electrons in the negative side and the holes in the positive side cannot flow from that one side to the other side of the PN junction diode. Here, the depletion region becomes it's like a wall. It's not allow the charges from one side to the other side. Okay, so immovable charges. It does not allow the charges from here to one side to another side. So it's called the depletion region. This is called the junction potential or barrier potential. Next we are going to see the junction potential or barrier potential. So after interchanging that electron and the holes in the other side, it repel the electrons to flow from negative terminal to the positive terminal, and positive terminal, the P side is repel the holes to passes from P to P side to the N side. So they are producing a barrier potential. So that it needs that energy to passes from P to N side or N to P side. So that equilibrium, that electron and protons are interchanges and produce the depletion layer up to that produce the equilibrium state. Up to that it will occur. After that it will stop after attaining the equilibrium. Then the difference in potential across the depletion layer is called barrier potential. So at 25 degrees Celsius, barrier potential is approximately equal to for silicon it is 0.7. Germanium is 0.3. So this is a barrier potential for the PN junction diodes. So PN junction diode is this thing. So this is a symbol of PN junction diode. See that P and N. One side is P, another one is N type. So this is a PN junction diode. It's a schematic representation. See, next thing is that conventional that circuit symbol. So the PN junction diode circuit symbol is this one. One triangle shape and one line is there. So this is called PN junction diode. So negative, that line is indicates the negative, that is called as cathode. That other triangle side is called anode, that is positive. So the direction of current flow from positive to negative, that is called conventional current flow. You know that. So next we are going to see that biasing a diode. So biasing means providing external energy to charge carriers to overcome the barrier potential and make them to move in a particular direction. I already told you that next the junction between the PN junction diode is producing a depletion region that is behaves like a wall. It won't allow the charge carriers from one side to that another side. Suppose the charges can pass from one side to another side, it needs that energy. That energy is given to the holes and the negative that is electrons to the potential, that is potential by using the battery we can apply, give the external energy. That energy, that external voltage is applied to the PN junction, what is called the bias voltage. Okay, so after applying that the voltage, that electron can pass from any one from negative to positive and positive to negative for the holes. So it's called biasing the diode. There are two types of biasing. One is the forward bias, another one is the negative bias. So screen, it is a forward bias. Forward bias means, you know that p-type semiconductor. P-type semiconductor means it contains large number of holes. That means positive charge. N-type semiconductor, it contains large number of electrons. That's why this is called N-type semiconductor. So N-type semiconductor is connected to negative terminal. P-type semiconductor is connected to positive terminal. So positive, positive and negative, negative. So negative electron to negative terminal. Positive to positive. So positive is connected to positive P-type semiconductor. Negative is connected to N-type semiconductor. So it's called forward biasing. When you are applying the forward biasing, what will happen? See, holes has the positive charges. We are connecting to the positive terminal. So what will happen? There is a repulsive force acting between the positive and the holes. At the same time here, the N-type is connected to the negative terminal. So the repulsive force acting between the electron and the negative terminal. So what will happen? It will repel to the junction. So the depletion layers become narrow. So ரெண்டு பக்கம் என்ன பண்றாங்க அப்படின்னா, that repulsive force is acting on that either side. So the depletion layer becomes narrow. So in forward bias condition, very small amount of energy is given to the charge carriers. It can easily penetrate through the depletion layer. So this is a function of the forward bias PN junction diode. So when we are applying that or increasing the applied potential of the current, that electron charge carriers are gradually increases. At a particular voltage, it is behaves like a conductor. It allows large number of charge carriers are passing through the depletion layer. Next one is reverse bias. Reverse bias means, you know that positive P-type is P-type semiconductor has the holes. N-type semiconductor has the electrons. So the P-type is connected to negative terminal. N-type is connected to positive terminal. See, positive to positive, negative to negative means that is forward bias. Positive to negative, negative to positive is called a reverse bias condition. So P-type semiconductor material is connected to negative terminal. N-type semiconductor material is connected to positive terminal of the plat. So what will happen? When you are applying the potential difference to the PN junction diode, there is an attractive force acting between that holes and the negative terminal. At the same time, electrons to the positive terminal. So what will happen? They are attract to each other. The depletion layers becomes wider. The depletion region is increases. So the wall is increases. So what will happen? Definitely the charge carriers cannot pass through from one side of the PN junction to the other side. Okay. So it is proven that by the depletion layer. So charge carriers cannot flow in this reverse bias condition. So current cannot flow in the reverse bias condition. Forward bias conditions, current can flow in the forward bias. The characteristics of junction diode in a forward bias. See here that is the PN junction diode. It's connected to the circuit here. It's a voltmeter and milliammeter. It's a resistance and it's a variable voltage. So positive terminal is connected to the negative terminal of ammeter and to the positive terminal. Now negative is connected to negative, positive is connected to positive. So here the diode is in a forward bias condition. So gradually we are increasing the voltage. So to measure the voltage, we are connecting the voltmeter here. To measure the flow of current, we are using the milliammeter here. So gradually the potential is increases. The flow of current also increases. So we can draw the graph between the voltage and the current. See the near the graph. So gradually the voltage is taken as the x-axis and current in the y-axis. So gradually the voltage is increases. The flow of current also increases. At a certain value, the flow of current is increases enormously in forward bias condition. See, up to this, it's behaves like an insulator. So behind that line, it is behaves like a conductor. It means that large number of charge carriers are passing through the depletion layer. In forward bias, you know that very small depletion region is there. So by applying the external energy, the charge carriers are passing through the PN junction diode. The flow of current is enormously increasing. So the graph shows that is like a conductor after that giving the high potential difference. So this region is called this voltage is called threshold voltage or cut-in voltage or knee voltage. So you can say that it's a knee voltage or threshold voltage or cut-in voltage. So from that we can conclude that breakdown voltage or the knee voltage for germanium is 0.3 volt. For germanium, for silicon is 0.7 volt. So the current flow is a very negligible, very small amount of current is flowing initially. After this potential, it increases very enormously. So it is behaves like a conductor. So in this graph, it's not a linear line, it is a exponential. So it is not obey the Ohm's law. We are not applying the Ohm's law for the forward bias condition. Next case, that forward resistance. Resistance, you know that R equal to V by I according to the Ohm's law. V equal to IR or R equal to V by I. So here reverse, that is resistance, forward resistance equal to delta V by delta I. Delta V is the change in potential. Say x-axis change in potential. In y-axis change in current. So using that we can calculate that forward resistance. So you have a practical. You can do that in a practical lab. So next thing is this diode behaves a conductor when it is in a forward bias. So in a forward bias it behaves like a conductor. Next thing is reverse bias. Reverse bias, everything is same. So see the circuit, everything is same. Only we are changing the diode. So initially it is connected to the positive terminal to the positive. Here now we are connecting the positive terminal of the battery is connected to negative terminal. Negative terminal of the battery is connected to positive terminal. So it is called a reverse bias condition. In reverse bias condition, again we can increase the voltage gradually. So the flow of current is very small. See, it is not a milliampere, it is a microampere. In forward bias, we measure the current in milliampere. But here we are measuring the milliampere, microampere. Mu means micro, you know that. So using that microammeter, we are measuring the current. So in reverse bias condition, when flow of current is gradually increases, the flow of current is increases very small current. That means no current is flowing in a reverse bias condition. Very small amount of current is flowing in a reverse bias condition. That current is called leakage of current. So it's called leakage of current. It's not a flow of current, it's a leakage of current. The leakage of current is produced due to the junction temperature. I already told you that energy is energy given to the PN junction diode, the conductivity increases. Like that, the junction temperature, due to the junction temperature, the covalent bond is broken, some small amount of charge carriers are produced. Due to that electrons are flowing in a reverse bias condition. So it produces very small amount of current. That current is called leakage of current. Okay. VI characteristics of PN junction diode. So now we are going to combine the forward bias and the reverse bias. See that we are going to take the relationship between the current through the diode and the voltage applied on the diode. It is referenced as a graph. This characteristics has every diode. X-axis represents the voltage applied on the diode and Y-axis represents the current through the diode. So potential and current. So right side is forward voltage region. So diode is forward biased. Left side is reverse voltage region. Diode is reverse bias. See that indicating the diagram. So positive is connected to positive, negative is to negative. So interchanging that value, it is become a negative. The diode has non-linear characteristics. When voltage is positive, current exponentially increases until it reaches the V0. So V0 is 0.7 for silicon and 0.3 for germanium. For voltage greater than V0, current rapidly increases and limited only by the resistance in circuit. You know that. So V0 is a rapidly increases based like a conductor. So it is not a linear, it's a non-linear. That's why I told you that the Ohm's law is not applicable for the PN junction diode. So in negative, there is a very small current is passing through that. It is not a flow of current, it's a leakage of current. When negative voltage is high enough, that current starts to flow through a diode in the reverse direction. The value of voltage is known as reverse breakdown voltage. So the reverse breakdown voltage is not occurs in this PN junction diode, but only it occurs in the Z0 diode. Okay. So this is a combination of the forward bias and reverse bias.